Hello, this is Dr. Rocío Pérez de Prado from the Telecommunication Engineering Department, the University of Jaén in Spain. Thank you very much for having me for this fourth international conference on educational technology and online learning. It's such a pleasure to present our work titled Optical Field Intensity and Power Analyzer in fiber-to-the-home clear networks for the comprehensive analysis of microbanding using smart devices. So this work has been developed by diverse professors and students from this telecommunication engineering department. It is also supported by a teaching innovation project in which I act as a main researcher. So basically, this is the index that I'm going to take into account, following the basic structure of the papers suggested by Ice et al. So we're going to make an introduction, make some comments on methodology, show the results, and then draw the main conclusions. So what is this work about? So this work is about optical fiber. We know that today optical fiber importance is absolutely remarkable. Not only because its importance in the market, but also because its importance in other technologies. It's something that is in the core of key technologies today in engineering, such cloud computing, IoT, 6G, mobile network, or 5G mobile networks, and so on. So the thing is that indeed for telecommunication engineering is such a key aspect to know the propagation of signal within these systems. And practically, it is a key aspect for telecommunication engineering students, the knowledge of its behavior in a client network. Okay, I say particularly for importance because here in Spain, many of our students, telecommunication students, that focused their work on optical communication, then they are most focused on what is clear networks, the deployment of fiber to the home networks. And within this network, it is such a key aspect, the microbanding of the fiber, because of the special characteristics of these systems. And it is so important that they learn to analyze the way the fiber, the light in the fiber is going to be propagated and the inherent losses to the specific infrastructure. So behind the idea of this word, we find this, okay? We know the main professional field for our students, and we know that it is key to know the propagation in a specific infrastructure, this client network. So basically, if we analyze the previous work, we find that it could be possible to find some propagation tools, but all of them are very limited. And indeed, if you take a look at them carefully, it is not possible, to the best of our knowledge, to find interactive didactic tools showing the spatial distribution of both field and power of these modes and show the confinement of the power within the core and the cladding, which is going to give us the clue about the resistance of a fever in the event of microbanding. So basically, we decided to extend some previous tool that we have developed, just to take into account the propagation of exact modes and linear polarized modes, and to extend it in a way that we could apply to microbanding in the study. Practically, okay, we extended using Guy MATLAB app, through the MATLAB designer. And also it was an intention not only that this tool is being able to be deployed in Windows and Mac OS systems, but also that this graphical interface could be deployed in smart devices such as iPad and touch bar screens, because it's much intuitive, and because our students now live in a world in which this kind of devices are so common that we might want to make them quite attractive for them, okay, to help them to use this and to motivate them to use it again. Okay, so first of all, we must bear into mind that the methodology is derived from the Maxwell equations from an electromagnetic study of optical fiber within a step index the modification of the refractive index within. Basically, considering this transverse distribution of the light, which is key to analyze the distribution and so the microbanding situation for this fiber and clear networks, we must take into account that there are two main index. Okay, so whenever we find a linear polarized mode, we're going to have FX index indicating us the number of field intensity maximums that appear when we go into a complete trance. That's mean 2 pi of in the fiber section, and then we'll have a second index which provide us the maximum intensity maxima that we can find from a cut from the axis to the core and the cladding. Okay, so once we are able to see the transfer intensity distribution of light, we're able to know exactly which one is going to be propagated. So we want to simulate this. We want to go from the equations for our linear polarized modes in our fiber. We want to show the students the fields. We want to show the fields. We want to make them receive somehow in real life and to be able to move these modes and to analyze this quite carefully. Not only the field, but also the intensity. And again, this is a key aspect, not only because it is quite intuitive and it is good for the learning to understand physically the form of these expressions, but also because this is absolutely connected to the nomenclature of this mode. So just visualizing one mode, you're able to see with exactly solution to the whole electromagnetic field you are obtaining. Okay, but again, it's not only something that we find that lacks in the literature. This visualization tools for intensity and field in optical fiber, but we also find that it's interesting to analyze VV curves. Okay, because sometimes, and also because of previous works, we've been able to offer the solutions to electromagnetic fields. But we want also to show the students that this electromagnetic field step in this optical fiber, it is very easy to be observed as a whole, not a specific for some specific parameters. That means for some specific radius, some specific refracting index for the core and the cladding, and also a predefined frequency, okay? But also that we can consider that we can give a general solution. So we can know in just one figure all the possible solution. And this is given by the VV curves. So again, we also want students to work within experimentally. So we want our tool to offer this possibility to solve in, to let the students see in just one graph the whole solutions, not just a specific one. So yeah, extending the possibility to see a specific for one value, and also this general perspective that this VV curves show us, and that are so important in the theory of electromagnetism in this field. Okay, so basically we're going to use the relations obtained from transcendent equation and energy values equations, and using numerical methods, we're going to be able to offer these curves. And this is going to be a very similar procedure in order to obtain power graphs. Basically, these graphs are going to give us for all the linear polarized modes, they're going to be able to give us the rate of power that we have in the cladding and the rate of power that we have in the core. Okay, so from here, it is very easy to see that when we go further in the normalized frequency, we are going to be able to obtain a much greater power in the core. So this means that the fiber is going to concentrate power much more in the core, and it is something that is going to make the propagation much safer in terms of losses, because power is not going to be dissipated when we find a curvature, a bending. Okay, so it is something good to see our students, that you are able to have a broad perspective of the technological parameters given by the normalized frequency, and this normalized frequency gives you the possibility to know the possible resistance of your fiber in this propagation condition to save or to be subject to these bendings. Okay, so here we have the results. So we are able to, first of all, to see that we have worked on this previous application where we analyze access mode and LP modes, and now we've been able to introduce some important improvements. Here we introduce the index for the modes that we want to analyze in terms of electrical field and intensity, and we have this calculate button. So we are able to graphically see, and also it is possible to move in 3D dimension of this perspective. And also, okay, because of the use of these numerical methods, once we have the specific value for the normalized frequency, also students are able to know what diagrams are possible for the what cubes. Okay, so this is the whole perspective that I was talking before. So just you have to introduce this normalized frequency, and then we have the analysis for this specific fiber. And also regarding the specific analysis of microbending, it is possible, again, to analyze which is going to be the percentage of power in the core and the power in the cladding, consider different conditions. Okay, so once we set the radio, we set the refractive index, and we have decided the working conditions in terms of frequency, we're able to give a value for the normalized frequency. And so we're able to observe exactly how many power is going to be concentrated in the core or in the cladding. Okay, so in this case, we see that we go along this normalized frequency from left to right, we're going to find that we're going to have a greater concentration, greater confinement within the core, which is going to give us a better properties, okay, for in terms of losses. Okay, so we can see these conditions for all the modes just with one graph, which is great. Okay, and again, we also intended to make this tool being able to be deployed in smart devices, in this case for iPads and Burberry touchable screen, that we have this photographs here. So the things that, okay, if students are used to use this type of devices, and it could perhaps be more attractive for them, so why not try to be careful in the side of the graphical interface in the way they're able to touch and to change the values in a more intuitive way. Okay, so as a conclusion, we could say that we have over a graphical and interactive tool for the learning of field intensity, propagation, and power confinement in a step index fiber, and especially focused for the students which are mostly interested in domestic fiber to the home networks in the last step, when we can find a lot of problems because of microbanding. We have developed graphical user interface, which is able to be deployed not only in my Windows and on macOS, such an extension of previous works, but also we have bear into mind the possible deployment in smart devices in a way that, okay, it is again more intuitive and more attractive for our students. And with all of this, we intend that we make more efficient the practical work, and we prompt the autonomous work, motivate students, facilitate the online learning, and foster participation of students through the use of these smart devices. Okay, so I think that's all. Thank you very much for your attention. I think that there are some ideas that my colleagues could find interesting. And so, same thing.